So let's come to our actual topic in linear programming problems, that is Simplex method. How to solve linear programming problems using Simplex method. The name is Simplex, but the process is a bit tedious, but you'll understand it by the end of this video. Let's have a recap of what we already know. First process is mathematical modeling. What is the meaning of mathematical modeling? I'm just giving you a hint. If you find it difficult to understand, you should go to my earlier videos and understand the whole concept. Mathematical modeling means to have mathematical expressions for the problems. For example, if I say that I have to sell 3 chairs and 4 tables, where x1 represents number of chairs and x2 represents number of tables. This is called our objective function, and what I want to achieve is I want to maximize my profit by selling these 2 items. This is what we speak in literally, that I want to sell 3 chairs and 4 tables. This is mathematical modeling of that. There are constraints. For example, there can be a constraint, like a constraint can be that at the most 1 chair and 2 tables is able to be accommodated in the shop. That is, this is the maximum limit that can be accommodated in the stores. So, and let's say the store is of 40 square feet. So we can say that this plus this can at the most accommodate 40 square feet. Or this can also be that this plus this actually equals to 40 square feet. So this is an equation form, this is an inequality form. This is how we actually do mathematical modeling of the problem. We have seen up till now, what we have seen is how to convert a mathematical expression into standard form. Now, second thing that we need to know is standard form of expression. If we have equations, we don't have any problem. The only thing is to consider there is that the variables, these x1, x2 and all, they should be greater than or equal to 0. If a variable is not greater than equal to 0, then let's say x2 is not greater than equal to 0, then what we do, we make x2 equal to x2 dash minus x2 double dash, where these and this is greater than equal to 0. So this way we actually transform the equation to standard form. Also, in case of inequalities, we use slack variables when we have less than equal to inequality, and we use surplus variable when we have greater than equal to inequality. So these 2 things you have seen, you know about these things. This I have discussed in my first video. Then we have started Simplex method in second video, where we have dealt with equations, that is problems which are in equation form. Now comes the actual challenge, that is Simplex methods for LPP, linear programming problems with inequalities, where we have inequalities. So the process is a bit long, but it is very easy once you understand. What I'll do, I'll start with an example and I'll give steps and solve the steps along with explanations. That is, I'll give theory plus example side by side, so that everything is very clear before you. Okay, so let's start with an example. This is our LPP, linear programming problem. We have to maximize z, which is equal to 4x1 plus 3x2 plus 6x3. The constraints are, first is this, 2x1 plus 3x2 plus 2x3 is less than equal to 40. Second is 4x1 plus 3x3 less than equal to 470. And third is 2x1 plus 5x2 less than equal to 430. x1, x2, x3 is greater than equal to 0. Okay. So, Simplex method, step 1. We'll use 6 steps to solve a problem. The first step, now you can see it on the screen. The first step, I'm reading it for you. Step 1 is expressing the problem in standard form. What you'll need to do, first of all, understand that only maximization is considered in Simplex method. So if you are given an objective function to minimize, what you can do is you can maximize minus of that z. That is, maximize minus z. So minimizing z means maximizing minus z. Then what you need to consider is the b's. That is, when you write in equation form, when you convert these expressions, these constraints which are in inequality form, when you convert them into equation form, you use slack or surplus variables. You should check that the b's, that b means what we have in the right hand side. So this should be positive. Here we have 440, 470, 430, they are positive. If we have a negative number, we'll multiply throughout by -1 to make the RHS positive. Okay, so this is the first step. Let's do it. We have to maximize, so no need to change to -z. We have to maximize. Okay, now first is this. We have three constraints, so we'll use three slack variables. Let's say s1, s2, s3. Let's use s1 here, that is 2x1 plus 3x2 plus 2x3 plus s1 is equal to 440. Then use s2 here, s3 here. What we'll do, we'll write all the expressions and use s1, s2, s3, those slack variables. How? First of all, we'll convert this objective function. This will now be 4x1 plus 3x2 plus 6x3, and we'll put the slack variables here. 0 into s1 plus 0 into s2 plus 0 into s3. 0 means it has no effect here, but this is the way to write so that we are able to create the simplex table. Now this function 2x1 plus 3x2 plus 2x3 plus s1, then we can write 0 into s2 plus 0 into s3 is equal to 440. This is first. Second is 4x1 plus 3x3 plus 0 into s1 plus s2 plus 0 into s3 equal to 470. Okay, then is 2x1 5x2 plus 0 into s1 0 into s2, here we'll have s3 equal to 430, where our x1, x2, x3 and these three slack variables s1, s2, s3, these all are greater than equal to 0, that is they all are positive. So we have converted this problem into standard form. Okay, so this is standard form. What I'll advise is you should keep doing this with me in your copy and pen. So use your pen and copy and keep noting these things so that everything is clear to you. So this problem, this LPP is now in standard form. Okay, so now we will enter our step 2. Up to here this is clear. If you have any doubt, you should go to my first video and see how we introduce slack variables. Clear? Now start with step 2. I am reading it for you. Step 2 is finding an initial basic feasible solution. If there are m equations with n unknowns, then assign 0 values to n minus m variables. That is, here we have how many equations? 3 equations, and the number of unknowns are 6. See, x1, x2, x3, s1, s2, s3. So n minus m, that is 6 minus 3, will assign 3 variables to 0. We'll assign 0 to them. Okay, so what we'll do, we will assign 0 to x1, x2, x3. Okay, they will be called non-basic variables because their value is 0. And our s1, s2, s3 that will start with in the initial basic feasible solution, they are called basic variables. Okay, so we'll now create a table. We'll create a table where the first column is CB. What is CB? CB column refers to the coefficients of the basic variables in the objective function. Then is CJ. CJ row denotes the coefficients of the variable in the objective function. Basis refers to the basic variables. For example, starting we have taken S1, S2, S3 as basic variables, so they'll be written in that column. Okay, so let's start with that table. I have written that expression to this side in a reduced form so that we'll use the terms whenever we'll need. We'll start with the table. The first column is called CB. I told you what is CB. CB has coefficients of the basic variables in the objective function. What is the meaning of this? Let me explain to you. Second column is called basis. This is it is the column which actually has the basic variables. I told you we have 3 constraints, that is m equal to 3, and number of unknown variables is 6, x1, x2, x3, s1, s2, s3. So we need to put n minus m, that is 3 variables equal to 0 at a time, so that we make them non-basic variables. So what we are doing in the first step, that is called the initial basic feasible solution, we'll put x1 equal to 0, x2 equal to 0 and x3 equal to 0. So these are non-basic variables in the initial basic feasible solution. So when these are non-basic variables, the rest, that is S1, S2, S3, they are basic variables. So we'll write S1, S2, S3. These are basic variables. So basis columns, basis column has elements that are the basic variables. So these are basic variables. What is CB? CB is the coefficient of this basic variable in the objective function. This is your objective function, C. And you can see S1, S2, S3, the coefficient is 0, 0, 0. So we'll write 0, 0, 0 here. Clear? Basis is the basic variables that we have taken, and CB, this column has the coefficients of these basic variables in the objective function. Clear? Then we write here Cj. Then we write the variables x1, x2, x3, s1, s2, s3, and we have b. B is the right side, 440, 470, 430. Okay? And here we have a row which is called Cj, small cj. Here what we did, we took the coefficients of the basic variable. Here we will take the coefficients of all these variables in the objective function. What is the coefficient? See, for x1 it is 4, so we'll write 4. For x2 it is 3. For x3 it is 6, and then we have 0, 0, 0. Clear what is Cj? So Cj is it is a row that contains the coefficients of these variables in the objective function. Clear up to now? Now we'll write the constraints. First constraint, 2x1, 3x2, 2x3, s1 1, and then 0, 0. This will be unitary, actually unit matrix. Why? Because 1, then 1 s2, then 1 s3. Now second constraint, 4x1, 0x2, 0x2, 3x3, s1 0, this is s2, and this is 0. Okay. Now last one, 2x1, 5x2, no x3, so 0, and then we have 0, 0, 1. Now we call this as body matrix. This one, this is called body matrix, and this is called unit matrix. See, this is a unit matrix. Okay, this is called body matrix. Clear up till now? So this is how we make the initial basic feasible solution table, and we'll write B here, 440, 470, 430. Okay, so this is our basic table. Clear? Now we'll move to step 3. Now let me read it for you. The third step is applying optimality test. We'll compute Cj, C capital here, which is equal to Cj minus Zj. Cj we have seen here, small cj, the coefficients of the variables in the objective function. So that's Cj minus Zj. And what is Zj? Zj is actually Cb. We have Cb matrix into the column matrix of the variable. I'll explain to you when I'll come back to the example. So it is Cb into Aij. Okay, and then we'll compute capital Cj. That is called we'll evaluate Cj, capital Cj, and that row is actually called net evaluation row. Cj row is called net evaluation row and indicates the per unit increase in the objective function if the variable heading the column is brought into the solution. We'll see it. Now, if all Cj are negatives, then the initial basic feasible solution is optimal. That is, when we'll have all Cj's negative, this means we have reached the optimal solution. That is the solution for which we'll have maximum z, that is the objective function. Obviously, for this, the table that we have just made, this won't give optimal solution. Why? Because x1, x2, x3 all are 0. So that cannot mean the optimum solution. So we'll compute zj and then we'll compute cj. If cj, all cj's are negative, then the initial basic feasible solution is optimal and we'll get the result. If even one cj is positive, then the current feasible solution is not optimal, and we proceed to the next step. Okay, so let's understand the example. So I told you we'll apply optimality test here. What is the meaning of optimality test? Optimality test means, first of all, we'll find a quantity that is called z. I'm writing it here, z. For each column, we'll find the value of Zj. J means the number of column, that is first column Z1, Z2, Z3, Z4, Z5. So we'll find Zj. And what is Zj? We write Zj as this Cb into Aij. What is the meaning I am telling you in simple word? Simple meaning is this is a matrix and this is a matrix. So this is row and this is column. So this into this, the way we multiply matrices. This into this. For first one Z1, when we have to take Z1, we'll do 0 into 2 plus 0 into 4 plus 0 into 2. Since we have all zeros here, so this will be 0. If it was 1, then obviously this would have been 2. Or if this was 1, 1, 1, this would have been 1 into 2 plus 1 into 4 into 1 plus 2. So that would have been 8. For whenever you will start, this will be 0, and so all Zj will be 0, because this is again 0 into 0, 0 into 0, 0 into 0. Okay. So Zj is 0, all. Now second, I told you capital Cj, that is your small cj, this one, minus Zj. So for C1, let's say this is Cj. So for C1, this will be this minus this, that is 4 minus 0, 4, 3 minus 0, 3, 6 minus 0, 6, then 0, 0, 0. See, all are positive. I told you in the step that with which we started, I told you that if these are all negative, then we have found the optimal solution. You can see these are not negative. So this is not optimal solution. Somewhere you will find this is taken as Zj minus Cj. So that is not an issue. There what we'll say? We'll say these all have to be positive. Because if this was Z minus C, this was minus 3, minus 4, minus 3, minus 6. So there what we'll do? We need to have all Cj greater than 0, all Cj positive, so that we reach feasible solution. So this was our step 3, that is we have applied optimality test. Since all Cj are positive, we know this is not our optimal solution. So now we'll go to step 4. This is your step 4. I am reading it for you. This step is identifying the incoming and outgoing variables. The variable in which Cj, we just computed capital Cj. So the variable in which Cj is maximum positive is the incoming variable. Okay. So for example, in our question, the maximum Cj is 6. So that variable, it is against x3. So that x3 is incoming. That is, in our next table, x3 will be entered. And which term will be exiting? That exiting term is called outgoing variable. What is it? We'll see. So the variable in which Cj is maximum positive is the incoming variable. This column is called the key column. If two Cj have same value, anyone can be selected. So if it was 6 and 6 in 2 columns, you can arbitrarily select any column. Then next is divide the elements under B column by the corresponding element of the key column. That is, the maximum Cj column is called key column. Now what we'll do in B column, we have elements in B column. We'll divide those elements by the corresponding elements in the key column. Okay. Now choose the row containing the minimum positive ratio theta. So theta will be B by x3 here. That is the element in B divided by the corresponding element of the key column. Now we'll choose that B which has the minimum positive ratio. Okay, and that row will be called key row. Okay. Now we'll replace the corresponding basic variable. That is, that variable will be outgoing. That is called outgoing variable. And in place of that variable, we'll bring in the incoming variable. I'll just explain to you in the example how to do this. Another thing to note here is the element at the intersection of the key column and key row, where these two intersect, is called key element. Okay. So up to now, remember, this is called key element. What we'll do, we'll see in the next step. If all these ratios are less than equal to 0, the incoming variable can be as large as we please without violating the feasibility condition. And the problem has an unbounded solution. So if all these ratios are less than equal to 0, I just told you the ratio, we are selecting the minimum positive ratio. But if all these ratios are negative, this means the solution is unbounded, and we'll stop there. Okay. So let's come up to this level and then we'll go to the next step. as I told you, this is the highest value of Cj. So the highest value of Cj, this column is called key column. It is, you can denote it like this by an arrow mark, or if you have highlighter, you can highlight this column. So this column is, what is this column? This column is called key column, and this variable, the variable of the key column, that is x3, that is incoming variable, that is in the next table will enter x3. Here we have s1, s2, s3, that is basic variables are s1, s2, s3. So in the next table, x3 will be a basic variable. Clear? Now, when x3 will be a basic variables, obviously we'll have one variable from here which will be exiting this table. That element is called the outgoing variable. And how to know, how to determine which is the outgoing variable? For that, what we do, we take theta, and theta is, I told you, b by, see, the element in the this column, key column. So theta here will be 440 by 2, that is 220. This will be 470 by 3, 470 by 3. So it will be roughly 165 something. I'm writing 470 by 3 only, okay? Let's not go to this. 470 by 3. And here we'll have 430 by 0. So this will be infinity. Okay? I told you, we'll select that value of this ratio, which is minimum positive. This is minimum positive. This we don't take into account. This is around 165. This is 220. So this is now our key row. Okay? So this is key column, this is key row. So this is key column, this is key row. Now key row, the variable is s2. So s2 will exit this table, and x3 from key column, this will enter here. So we'll take this out and we'll enter x3. So x3 is called incoming variable, s2 is called outgoing variable. Okay? So clear up to now? And one more thing, we have a term called key element. We know key column, we know key row. Where they intersect, see here they are intersecting, the key column and key row. This element is called key element. Up to this step, step 4, this is what we have to do. Now we'll enter step 5. It says iterate for optimal solution. What we'll do, enter the incoming variable with its associated value under CB column. Okay? Obviously, when x3 will enter the basic variable, that is when it will enter basis, then it will come with its coefficient. The coefficient in objective function is 6. So CB will be 6 for x3. Okay. Then next is convert the key element to unity. We'll have to convert the key element to unity, that is 1, by dividing the key row by the key element. Obviously, our key element is 3. So what we'll do, we'll divide the entire column by 3. Okay. So that this is, the key element is 1 now. Now, make all other elements of the key column 0. We have other 2 elements. We'll have to make them 0. How? By elementary row transformation. That is, you know, in matrix, R1 will apply on R1, R1 minus, let's say, 2R2. Like that, we'll make all the elements 0. Now, by subtracting proper multiples of key row, we'll make all the other elements of that column equal to 0. Okay. Now we'll see, again we'll see what is the value of Zj and Cj. If all of them are negative, then we have reached the feasible solution, optimal solution. But if not, we'll restart. That is, again we'll find the key column and the key row, and we'll restart. We'll have incoming variable and outgoing variable. Okay. So what we'll do, this s2 will be out now. S2 out means now this will become non-basic variable, that is s2 equal to 0, and x3 will come to this point. Okay. When x3 comes, we'll have to put its coefficient. The coefficient of s2 was 0. The coefficient of x3 is 6. Okay. Now what I told you, we have to make this 1. How can we make this 1? Only by multiplying this body matrix and unit matrix from here to here on, here to here, up to b. We'll multiply by 1 by 3. When we'll multiply by 1 by 3, this will become 1, 0 by 3, nothing. This is 4 by 3. This is 1. So 1 by 3. This is 470 by 3. So we have our this. Now what I told you in the key column, we'll make other elements in the key column equal to 0. See, here up to this point, only this is non-zero. This is 0, so no need to think about this, but this is not 0. So what we'll do? This is row 1. What we'll do? Row 1 minus 2, row 2. That is, this 2 minus 2 will be 0. So let's start with this. This is 2. What I am doing? I am doing row 1 minus 2, row 2. Okay. So row 1, this 2 minus 2 of this. That is 2 minus 8 by 3. This is 6 minus 8 by 3. So this is minus 2 by 3. So this term will be minus 2 by 3. Okay. 3 minus twice of this. So it remains 3. 2 minus twice of this. So this becomes 0. Okay. 1 minus twice of this. The same. 0 minus twice of this. So this is 0 minus 2 of this. So this becomes minus 2 by 3. 0 minus 0. Nothing. This minus twice of this. See, this will have to do 440 minus twice of this. Twice means this is 940. Okay. So 940 by 3. 450, 450, 900 and 20, 20, 40. So this. Now here. See, this is 1200 and 120. So 1320 minus 940 by 3. Now this will be 320 plus 60. So 380 by 3. So here we'll have 380 by 3. We need to do this because this is the value of this variable. Finally, when we'll have our optimal solution, x3 will be this. If this is s1, this will be this. So we have to keep doing this. Okay. Now let's start again. We'll find zj and we'll find cj, and we'll see whether these all are negative. Okay. So zj is, I told you, this into this. See, this into this 0 plus this into this. 3, 6, 2, 4. So this will be 8. Okay. Then 0 into 3, 0, 6 into 0, 0, 0. So this is 0. This one, 0 into 0, 6 into 1. So this is 6. This one, 0 into 0, 6 into 0. So 0. This is 0 into 0, 6 into 1 by 3. So this is 2. Then 0, 0, 0, 0. So this is 0. So this is our zj. Cj will be this minus this. So 4 minus 8. 4 minus 8. That is minus 4. 3 minus 0. 3. 6 minus 6. 0. 0 minus 0. 0. 0 minus 2. 0. Now, still we have this 3. We have minus here, but this is 3. See, we have a positive element here. So again, because this is maximum, this will become your key column. Okay, so this is your key column. We'll do theta. Theta will be, key column is this. So this will be by this. So 380 by 9. This is your theta. This is 470 by this. So this is infinity. This is 430 by 5. 430 by 5. So which is the least value? Let's see, this will come to roughly 38 or something. This will be 70, 80. So this is the least value. So this is our key row. Now, key row means this is outgoing variable and key column means this x2 is incoming variable. So now x2 will come to this point and s1 will exit. Clear? And the key element here is, see, this and this. So again, this is the key element. Okay. Clear up to this? So since we have not got Cj, which are all are negative, each Cj has to be less than or equal to 0 so that we reach the optimal solution. It's not the case. So what we'll do is, we'll restart. Our entering variable is x2 and exiting variable is s1. Okay. So our step 6 is, since all the Cj, capital Cj, are not equal or less than 0, less than or equal to 0, that is, they all are not negative, therefore our solution is not optimal. So what we'll do, we'll again go to step 3, restart from there. That is, again find our key column, key row, key element, and we'll do this process again. We'll keep on repeating this process till we get our all Cj is negative. So let's see. So here what we'll do, we'll introduce x2 here. So let's see x2. So along with this, what we'll do, we'll put this coefficient in the CB column. This is 3. Okay. Now what we have to do, we have to make this 1. Remember, we have to make the key element 1. So dividing the row by 3. So this is 1, This will be 2 by 3. So dividing by 3 means 2 by 9. 0 by 3. This is 1 by 3. This is again 2 by 9. And this is 380 by 9. Okay. So this step is done. Next step, what we used to do, we have to make all the columns other than this 0. See, this is 5. So we have to make it 0. What we'll do? This is row 3. So we'll do as row 3 minus 5 of row 1. 5 of row 1. Okay. So let's start. This minus 5 of this, that is 2 minus minus plus 2 plus 10 by 9. 2 plus 10 by 9. So this is 28 by 9. So here we'll get 28 by 9. Okay. Then 5 minus 5. So this is 0. 0 minus 0. 0 minus 5 of this. So this will become minus 5 by 3. 0 minus 5 of this. So this will now be plus 10 by 9. Okay. Minus minus plus. So 10 by 9. Then we have this one. 1. 1 minus 0. So it remains same. 5 of this. This minus 5 of this. See. 430 minus 5 into 380 by 9. Okay. So let's do it. So this will be 430 cross 9, that is 3870, minus we have 380 into 5, that is 1900 by 9. So this is 3870 minus 1900, that is 1970 by 9. 1970 by 9. Okay. So here we'll write 1970 by 9. 1970 by 9. Okay. Is it divisible by 9? No. Okay. So this is our table now. Let's restart. Let's identify Zj and then Cj and see if all are negative. Okay. So let's start with this. This is this into this. So we'll have, see, minus 6, 3 into 2. So minus 6 by 9 plus 6 into 4 by 3. 6 into 4, 24 by 3. Okay. So this is the first term. This is 0 into 0. So we can write it like this. This is 3, 2, 3, 3. So we can write 24 minus 2. That is 22 by 3. So this is 22 by 3. Okay. Then come to this. 3 into 1, 6 into 0, 0. So 3. 3 into 0, 6 into 1, 6. 3 into this. So 1, 0. So this is 1. Then 3 into this plus 6 into this. 3 into this. So this means 6 by 9. Again 2 by 3. Okay. This is minus 2 by 3. This is 6 by 3. That is plus 2. So what we get? We get 6 minus 2 by 3. So this is 4 by 3. So here we'll get 4 by 3. Okay. No. 0 minus, what is this? Zj is this into 0 into 0. So this is 0. Okay. Now Cj, this minus this, that is 4 minus 22 by 3. 4 minus 22 by 3. 4 minus 22 by 3. This is 12 minus 22 by 3. This is minus 10 by 3. So here we have this as minus 10 by 3. 3 minus 3. So this is 0. 6 minus 6. 0. 0 minus 1. So this is minus 1. 0 minus 4 by 3. So minus 4 by 3. 0 minus 0, 0. Now you should check this. See, all the terms, all Cj, each Cj is less than equal to 0. See, either it is 0 or less than this. This means this is minus 10 by 3. This is minus 1. This is minus 4 by 3. What is the meaning of this? It means our optimal solution, we have reached our optimal solution. So this is the optimal solution. Now, so what is the value of the variables? Value of the variables is, see, we have x2 and x3 here. x1 is still here. So x1 is 0. That is the variables, the value of the variables for this to be optimal is x1 equal to 0. x2 is equal to 380 by 9. I told you this will be the value of that variable. So this is 380 by 9. And x3 is x3 is 470 by 3. 470 by 3. So this way we have reached our optimal solution, and from here we get that z will be maximum for x1 equal to 0, x2 equal to 380 by 9 and x3 equal to 470 by 3. And the value will be, what you will do, you will put 4 into this 0, 3 into this plus 6 into this. Okay, so I am now, this is clear to you, you must have noted it down. Now I am rubbing this. So our maximum z max will be 0 into x1, so 0 into 4 plus 3 into x2, see 3 into 380 by 9 by 6x3, 6 into 470 by 3. So let's say this is by 3, so let's have the value. So the value will be 380 plus 470 into 6, 470 into 6, that is 2820 by 3, 2820 plus 380, that is 3200, that is 3200 by 3. This is the value of maximum z. So this is how we do computation in simplex method. When you do this for first time, it will you'll feel this is very difficult. It's not difficult. I have given you 6 steps. You have to go step by step. First step, convert it to standard form. Second step, make the initial feasible, basic feasible table. Then find zj and cj. If all are less than or equal to 0, then only you have this optimal solution. We know in the first table that is not the case, because there we'll have x1, x2, x3 all 0. So the column with maximum cj, that will be key column. Then here what we'll do, we'll take theta, that will be b by the corresponding element of the key column. Now the minimum positive value of that of theta, that will be key row. If all those ratios are less than equal to 0, that means the solution is unbounded. So we'll stop and we cannot do anything further. But otherwise, what we'll do, the minimum positive value theta, that will be key row. So we'll identify the key element. Okay. Now that variable which has key column, that will be incoming, and the row, the variable that has the key row, that will be outgoing. So we'll bring that variable into this basic variable and we'll exit the outgoing variable. Then repeat the process. How? First of all, we'll make the key element equal to 1. How? By multiplying the row by 1 by key element. So we'll get it. Now other elements in the key column, we'll have to make it 0. How? By elementary row transformation. Well, one element is your key element, the other 2 elements you have to make them 0. Row 1 minus 2, row 2, row 2 minus row 3, whatever it be. If the number is 2, so that row minus twice of that row, the key row. We'll get it. Now we'll again find zj and cj. If each cj is less than equal to 0, our basic, our optimal solution is reached. If not, we'll repeat it. We'll keep repeating it until we get the all cj's as less than equal to 0. We'll have our optimal solution, and the value in the b column will be that variable. Okay, the way we saw it, and then we'll put it in the objective function and we'll get the maximum value of that function. Okay.